So it's now week 12, and we're going to talk about a new chapter called Laplace Transform. Okay, this is a totally separate chapter from the Fourier series that we talked about. Okay, so what is Laplace Transform? Laplace Transform. So Laplace Transform is a technique to convert time-dependent functions into frequency-dependent functions. Okay, in other words, you're converting a function from time domain to frequency domain. Okay, it sounds very abstract at first. Okay, you might not know what I'm talking about, but bear with me. Okay, so a technique to convert, okay, from the time domain to the frequency domain. Okay, so that's what it means. F of t is the time domain, right? Because you see, f is a function of t, which is time. Okay, time domain. Whereas s here refers to frequency. Okay, it is the frequency domain. Okay, so t refers to time, okay, time as your variable, and s refers to frequency as your variable. Okay, but strictly speaking, it doesn't need to be time, okay? And more broadly speaking, right, why do we learn Laplace transform? Okay, the goal behind Laplace transform, right, is to help us solve differential equations. Okay, solve differential equations. Okay, very simple differential equations. And to be specific, I'm talking about linear ordinary differential equations. Okay, so these are like the simplest case of differential equations. Okay, so we're not going to explore very complicated cases of differential equations. So Laplace transform is a technique to convert f of t to f of s. Okay, and what it helps us does eventually is to solve differential equations. Okay, linear ordinary differential equations. But this will be the subject of the next week. For now, what we are what we are interested in is getting you comfortable in performing Laplace transforms. Okay, we need to be comfortable in converting f of t to f of s and f of s back to f of t. Okay, so we also need to do the inverse of the Laplace transform. Okay, so that's our focus of this week. It is to get comfortable with doing Laplace transforms and inverse Laplace transforms. Okay. Okay, so we need to know some properties of Laplace transform. So here we have the definition of the Laplace transform. Okay, so suppose I give you a function y of t. Okay, so y is some variable that depends on time. Okay, for example, a man is walking some distance, right? His position y is a function of time, right? As time changes, his position changes. So this is a simple example in engineering that you might use the Laplace transform in. Okay, so y is a function of t. Okay, if I take the Laplace transform of y, okay, I take the Laplace transform. Okay, so what you do, how you denote Laplace transform, right, is this, the curly L. So this refers to Laplace transform. Okay, so now I'm taking the Laplace transform of y, and what will I get? I will get big Y of s. Okay, so this is our notation for Laplace transform. Time-dependent functions are lowercase. Frequency-dependent functions are uppercase. Okay, time-dependent functions are lowercase. Frequency-dependent functions are uppercase. So maybe I give you a different function, say f of t. Okay, if I take the Laplace transform of f of t, what I'll get is big F of s. Okay, if I give you g of t, I take the Laplace transform of this function, I'll get big G of s. Okay, so this is our notation for Laplace transform. So big Y, big F, big G are our Laplace transforms of Y, F, and G respectively. Okay, so the next property is called the linearity. Okay, the linearity uh, property of Laplace transform. So Laplace transform, let me just quickly write it. Laplace transform is a linear operator. Okay, so what does it mean by to be a linear operator? Okay, if it's a linear operator, it satisfies this property. Okay, so let's take a look at this property. So let's focus on the left hand side first. So on the left hand side, we have this uh, a times f of t plus g, sorry, plus b times g of t. So f and g are time dependent functions. A and b are just constants multiplying f and g respectively. So we say that the Laplace transform is linear, right? What that means is I can distribute uh the Laplace transform to the first term and the Laplace transform to the second term. Okay, this is just like differentiation. Okay, remember differentiation? Okay, suppose I give you fx squared plus 2x. See, when you let the derivative operator act on this expression, the differentiation will act on the first term and the second term. So that's what I mean by linear. So you can also say differentiation is a linear operator. Likewise, Laplace transform is also a linear operator. So I can let the Laplace transform act on the first term and the second term. So what we'll get, right, is this. So Laplace transform A f of t plus Laplace transform of g, sorry, b g of t. And then what you can further do, right, because these are constants, since these two are constants, you can pull them outside the Laplace transform. You can pull them outside the Laplace transform. So what you get at the end of the day is A times the Laplace transform of f plus b Laplace transform of g. Okay? So let me recap again. Laplace transform is said to be a linear operator. Okay? So what that means is, first, you can let the operator act on the first and second term. And then when you do that, you can remove the constants outside the Laplace transform. And strictly speaking, it must be constant, okay? So if I give you, for example, Laplace transform of t, f of t, right? You cannot pull this t outside here. Okay? You cannot do that because t is a variable. This is a variable, not a constant, okay? It is not a constant. So you cannot just pull it out like that. So this property only works for constants. Okay, so that's the linearity of the Laplace transform. And it's just very much like differentiation, right? Okay, so like I said earlier, we have differentiation of, let's say, 10x cubed plus 5x squared. Okay, first things first, you can let this act on each of them. dx 10x cubed plus dx 5x squared. And then constants can be pulled out, right? So constants can be removed and constants can be removed. Okay, so very similar to differentiation and integration, actually. And you'll see why. Okay, you'll see why this property is valid. So in Laplace transform, we have this very important table that's given to you in exams. Okay, so this is called the Laplace transform table. So what does the table show? On the very left column here shows elementary functions. Okay, so elementary functions are common functions that we see a lot, okay, in, for example, engineering application. Okay, so these are very common basic functions. So for example, 1, okay, 1 is a very common thing to see. Or for example, t to the power of something. Okay, so this is t to the power of something, t to the power of something. Very common function that you see, and so on and so forth. See, we have sine, cosine, sinh, cosh, and then this is called the unit step function. But we'll not talk about that. We'll talk about it in some other time. Okay. So what does this table say? On the left-hand column, we have common functions, and on the right is their respective Laplace transform. So what does this mean? So let's take a look at the first row. Okay, let's take a look at the first row. The first row says Laplace transform of this will give me this. The second row says Laplace transform of this will give me this. The Laplace transform of this will give me this, and so on and so forth. Okay, so the Laplace transform of the left-hand column will give you the Laplace transform of the second column here. Sorry, let me say that again. The Laplace transform of the left column will give you the entries in the second column. Okay, will give you the entries in the second column. Okay, So what you need to know, right, is what you get from this table is the information. Okay, let's take a look at the first row first. Okay, so Laplace transform of 1 is equal to 1 over s. Okay, let's take a look at the second row. Laplace transform of t to the n minus 1 is equal to n minus 1 s to the n. Okay, sorry, factorial. Okay, and I'm going to do another example for the third row. So the third row says Laplace transform of t to the n minus 1 e to the at is equal to n minus 1 factorial s to the a. Okay, so this is how you use the Laplace transform table. Okay, you're given some function, you want to find the Laplace transform, you refer to the second column. Okay, so down here is just some other functions. Okay, nothing different. So the Laplace transform of the left hand side will give you the right hand side. Okay, so these are just other functions. Okay, and the Laplace transform table will be given in the exam. Okay, another skill set that you need to know for Laplace transform is partial fraction decomposition. Okay, you'll see this a lot when you do the problems related to not partial fraction. I mean Laplace transform. You involve the partial fraction decomposition. Okay, so you need to know how to do partial fraction decomposition. Okay, but before we do that, right, we need to talk about uh polynomials. So I know some of you might forget what polynomials are already because it's been a while since we touched it. So if f of x is said to be a polynomial, okay, it takes on the form of okay, a naught plus a1 x1, sorry, a1 x to the 1 plus a2 x to the 2 plus so on and so forth, an x to the n. Okay, so you already seen this before, okay, right? You already seen this before. So polynomials must be very familiar to you. So we also need to talk about the degree of a polynomial, okay? The degree of a polynomial, okay, the degree of a polynomial refers to its highest power. Highest power. Okay? So let's say I give you a second order polynomial. Second order polynomial. Okay? Then that means we have the function a2x2 plus a1x to the 1 plus a naught. You see, the highest power is x to the 2, right? This 2 is what I'm referring to. So we say that this polynomial has an order of 2. Okay, let me give you a different example. So let's say ax cubed plus bx5 plus cx4. Okay, so what's the order of this polynomial? The order of this polynomial is 5, right? It is a fifth order polynomial because the highest power is 5. Okay, so that's how we look at polynomials, okay, and their orders. Now, let's also talk about polynomials, okay? I'm going to talk about polynomials starting from 0th order to the second order. Okay, that's enough for our discussion for now. Okay, so what is a 0th order polynomial? Okay, a 0th order polynomial is what we call a constant. Okay, a constant. So see, if it's 0th order, right, that means f of x is equal to a naught. So it's just a constant. I mean, this is a fixed number. Okay, for example, 5 is a constant, right? Another example, 17 is a constant. Okay, it's just a number letter. That's it. Okay, that's it. So nothing interesting. So that's a 0th order polynomial. Now, what about a first order polynomial? Okay, so what do you call a first order polynomial? You call this a linear polynomial, right? So let's take a look. F of x, okay, if it is a linear polynomial, it would be a naught plus a1x. Okay, so I'm talking about only up to here. Okay, the first order polynomial. Why is it first order? Because it's the highest power of 1. Okay, so why is it called linear? You remember straight lines, right? Straight lines take on the form of y equals to mx plus c. This is in the form of y equals to mx plus c. See, this is y equals to mx plus c. Okay, so this is c, this is m, and that's x. Okay, so that's why you call this a linear polynomial. Okay, so if it's highest power 1, then it is a linear polynomial. So this maps out a straight line. Now let's take a look at the second order polynomial. Okay. So second order polynomial is what you call a quadratic. Okay, quadratic polynomial. Okay, so let's take a look at what a quadratic polynomial looks like. So a naught plus a1x plus a2x to the 2. So you see, it's highest power 2, so therefore it has order 2. So we call this a second order polynomial. Then this is already very familiar to you, right? You already learned quadratic functions since secondary school, which is, in the form of ax squared plus bx plus c, right? This is ax squared, bx, and c. Okay, so this is already very familiar to you. Okay, and don't forget, right? Quadratic polynomials can be written in a special form called completed square form. Completed square form. Okay, and generally it takes on the form of a x minus h squared plus k. Okay, so we will talk about this later. Okay, I'll talk about how to do this, so don't worry. I just want to get you clear on what is a constant, what is a second, sorry, what is a constant, what is a linear polynomial, and what is a quadratic polynomial. Okay, so this one has power 0, this one has power 1, and this one has power 2. Okay, now why do I introduce you polynomials? Because it will be helpful in partial fraction. So you see, partial fractions, right, always involve rational functions. Okay, rational functions, okay, from the name itself, rational comes from the word ratio. Ratio means fraction. Okay, and where do you see this fraction? See, rational functions are a fraction of two functions. See, this is function divided by a function. Okay, function divided by a function, function divided by function, function divided by function, and so on. Okay, more specifically, right, these are polynomials divided by polynomials. See, polynomial divided by polynomials, polynomial divided by polynomials, polynomial divided by polynomials, and so on and so forth. Okay, so now let's do a little exercise to identify what are we looking at. So what do I mean by what are we looking at? Okay, I'm going to ask you, is it a constant, a linear polynomial, or a quadratic polynomial? So take a look at this. At the top here, what is this? Is it constant, linear, or quadratic? Because this is the form of mx plus c, okay, highest power is 1, so this is linear. Okay, up here is linear. What about this factor here, x minus a? Is it constant, linear, or quadratic? Because the highest power of x is 1, you know that this is linear. Okay, same with this. Highest power is 1, so this is also linear. Okay, now let's say, for example, this. What is a? Is it constant, linear, or quadratic? Because there's no x, right? Which means it's x to the 0. Therefore, this is a constant. Okay, likewise for b. B is a constant. Okay, c is also a constant. And what else? This, see, the highest power is 2, so this is a quadratic polynomial. Okay. Now that we are familiar with the terms, okay, constant, linear, quadratic, we are able to easily talk about partial fractions. So the main question to ask about partial fractions, and by the way, this table is not given exams, okay? Not given exams. The main question to ask yourself, right, when doing partial fraction is, you are given this, okay? You are always given this left-hand side. How do you know how to write the general form of the decomposed form? Okay? This is the general decomposed form. General decomposed form. General decomposed form. Okay, decompose means you break it down. Form. You break it down. So how do we write this? Okay, this is a mysterious question of how to write this. So let's take a look at the left-hand column. Okay. Now we want to find the decomposed form. So here we have the general decomposed form. Okay, so let's take a look at number one. Number one, okay, we have a linear polynomial divided by two linear polynomials. Okay, so the main rule to write general form, the general decomposed form is this. Okay, you factorize the denominator fully. Okay, see, this is fully factorized, fully factorized, fully factorized, fully factorized, fully factorized. Okay, this is factorized as much as possible. First, you need to fully factorize the denominators. After you fully factorize the denominators, right, the general decomposed form, right, is done by writing each of the factors. Okay, so what I mean by factors, I mean this. Okay, so this is a factor, and this is a separate factor. Okay, in here, there are two repeating factors. See, because this is power 2, this is x minus a, x minus a. Okay, so these are repeating factors. Then here there are three factors, right? 1, 2, and 3. Okay, and so on and so forth. Okay, so what you need to do is you write out the factors as separate denominators first. Okay, you write out the factors as separate denominators. So in the first question, what are the factors? This one and this one, x minus a and x minus b. So you write them out separately first, x minus a plus x minus b. And then what do you fill at the top? What you fill at the top, right, is a polynomial which is one power, okay, one order less than the bottom. Okay, let me say that again. What you fill at the top is a polynomial that is one order less than the bottom. Okay, let's take a look at the bottom. This is a first order polynomial. One order less than that is a constant, right? Remember, you always go from constant. Sorry. So constant is power 0, linear is power 1, and quadratic is power 2. Okay, so the x minus a is linear. So one power less than that will be a constant. So what you fill up here, right, is just a. Okay, a represents a constant. Now look at x minus b. This is a linear polynomial. One order less than a linear polynomial is a constant. So you also put b. Okay, it represents a constant. Okay, so this will be the general form of the first example. Now take a look at the second one. So the second one, we have repeating factors. Okay, so repeating factors, there's a special method to do this. What do you need to do? Okay, you see, what you need to do is you need to build up the denominator. So what do I mean by build up the denominator? You need to build up the powers until you reach the power of the denominator. So what I mean is this. You see, this is a repeating factor, right? In the case of repeating factor, what you need to do is, okay, since this is 2, I need to stop until power 2. Okay, so let me show you what I mean. So for this question, you need to write first x minus a, followed by x minus a to the power 2. Okay, so you see, because down here, the factor repeated twice, right? I need to build up until it reaches the power 2. So here, actually this one is power 1. Then the next one will be power 2. Okay, so let me give you a similar example. So let's say, instead of power 2, okay, instead of power 2, let's say now this is power 3. So what would that look like? What it would look like, right, is this. Okay, so first will be x to the a to the power 1. Next will be x minus a to the power 2. The next will be x minus a to the power 3. You see what I mean? Because this is 3, right? I need to keep accumulating it until it reaches x to the 3. So this is x minus a to the 1, x minus a to the 2, x minus a to the 3. Okay? So let me give you a similar example. So suppose now this is 4. Okay, now you need to accumulate it all until up until 4. Okay, so now first one is x minus a to the 1. Next is x minus a to the 2. Next is x minus a to the 3. And finally, it is x minus a to the 4. Okay, so this will be the decomposed form. I mean, we haven't filled this up yet, but how do you fill this up? Okay, so to fill up the numerators, right, it will be, again, a polynomial which is one order less than the bottom. Okay, one order less than the bottom. But in this case, right, it is one order less than the bottom before further powers are applied. Okay, before further powers are applied. Okay, so what do I mean? Okay, one order less than this is a constant. What about this? Is one order less than this linear or a constant? See, that's why I say before further powers are applied. Okay, so the answer here is it must be a constant. Okay, why? Because I'm not looking at this as a whole. If you look at this as a whole, right, this is quadratic. Why? Because there's a power 2 here. So this should be quadratic actually. But since the rule is that you take one power less than the polynomial before further powers are applied, okay? Before further powers are applied. So you don't look at this because this is the further application of a power. So what you look at is inside the bracket before further powers are applied. So this 2 here is what I'm talking about when I say further powers are applied. Okay? So you only look at x minus a, which is linear. What is a polynomial 1 degree less than linear? Then it will be a constant. Okay, same with here, before further powers are applied. So this is a constant. Same with here, before further powers are applied. So this is a constant. So that's how you write the decomposed form for a repeating factor. Okay, so for repeating factor, you need to build up the powers in the denominator first, and then after that, in the numerator, you fill up 1 degree less than the denominator before further powers are applied. So this is A and B. So let me check our answer here, because I don't want to mess up. Yeah, I'm correct. Okay, let's look at the next one. So the next one, okay, first write out the separate factors. So as the denominator, so x minus A plus x minus B plus x minus C. Okay, and then at the top here, remember, one order less than the bottom. One order less than the bottom. So all of these are linear, right? Then one order less than the linear is a constant. So all these are just constant. A, B, C. So let me check if it's correct. Yeah, it's correct. Okay. So next. Okay. So here we have a repeating factor and a standalone factor. Okay. So remember, for repeating factor, you need to build up the powers. Okay. So first you need to build up the powers. So start from x minus a to the 1. Next is x minus a to the 2. It only repeated 2 times, so you only need to accumulate until 2. Okay, then lastly you have the x minus b. Okay, then what do you fill at the top? You fill up a polynomial, which is 1 degree less than the bottom before further powers are applied. So this is a, b, and c. Okay, then lastly, what about this? Okay, not all quadratic polynomials can be factorized, right? Some can be factorized, some cannot. Okay, for example, x squared plus 2x plus 1 can be factorized, right? Let me check. X 1 1. Yeah. Okay. So this can be factorized. However, not all quadratic functions can be factorized. For example, I'll give you this. Right? This cannot be factorized. Okay. So down here shows an example of a quadratic factor which cannot be further factorized. Okay, so what do you do in this case? It's just like before. So first, copy out these two factors as separate fractions. Okay, separate fractions. Next, what you need to do is fill up the top. And what is the top? The top is always 1 degree less than the bottom. Okay, the top is always 1 degree less than the bottom. So you see, this is a linear. 1 degree less than that is a constant. This is a quadratic. So 1 degree less than a quadratic is a linear. Okay, so that's why it must take on the form of bx plus c. And why is this linear? Because the highest power is 1. Okay, so this is how you write a general decomposed form. Yeah. Okay. Yeah. So this is how you get an idea of how to do partial fraction decomposition. Okay. The next property that you need to know is that Laplace transform is an invertible operation. Okay, is an invertible operation. So I already told you that Laplace transform of y will give me big Y. This process can be reversed. So if I bring the Laplace transform to the other side, so what it will show me is y is equal to Laplace inverse of big Y. In other words, right, if you want to find y of t, what you can do is take the inverse Laplace transform of y of s to give you back y of t. Okay, so this is an invertible operation. It means it can be reversed. Okay, so you know that it can be reversed, right? So let's go back to the Laplace transform function. So taking the Laplace transform, right? Okay, if I want to take the Laplace transform of f of t, means I'm going from the first column and transforming it to the entries of the second column. Whereas Laplace inverse will be the opposite. Okay, the Laplace inverse. So now I want Laplace inverse of f of s. It'll be the other way around. So what it means is, okay, taking the Laplace transform of big f of s means I will convert the entries of the second column into the entries of the first column. So let's see what I mean. So let's consider the first row. If I want to take the Laplace inverse of 1 over s, this will give me 1. Okay, so Laplace inverse of this will give me this. Okay, likewise in the second row. So let's take a look at the second row. So I want to find the Laplace inverse of this. Laplace inverse of n minus 1 factorial s to the n will give me the first column entry t to the n minus 1. Okay, and so on and so forth. So this is how you make use of this table to first find Laplace transform, and then secondly to find the Laplace inverse of frequency domain functions. Okay. Yeah. Okay. So I'm not gonna go through this example because it's fairly obvious. So yeah, we can straight away start the questions. So here I have the table prepared for me. Oh, by the way, right? By the way, how you might wonder, how do people get this, right? It's not clear or explained well. How do people obtain this? And how people obtain this, right? And particularly how Laplace obtained this. So Laplace, right, is the name of a mathematician. I believe he's a French mathematician. Yeah. Anyways, he's the mathematician who created the Laplace transform. So how did Laplace obtain these functions? Okay, so what he did is these elementary functions, right? So what you see here in the entry of the left column, okay, the first column, what he did is he put it into this Laplace transform definition. Okay, he created this formula, and then what he did is, for example, let's take a look at the first row. Okay, what he did is, see this, f of t is equal to 1, right? What he did is he subbed this into here. So he subbed 1 into here, and then after doing a lot of math, he obtained, okay, he obtained the result 1 over s. Okay, and then after that, he put this into the second column. Okay, let's take a look at the second row. Okay, so Laplace wanted to find the Laplace transform of this. Okay, Laplace transform of this. So in order to obtain the second row expression, what he did is he replaced this f of t with t to the n minus 1. Okay, and then he did some derivation. And eventually, he arrived at the result n minus 1 factorial over s to the n. Okay, and then he put this result into here. Okay, so this is how Laplace obtained these results. Okay, but our interest is not the derivation of this. Our interest is how to make use of this table. Okay, so this has already been obtained by Laplace, by the mathematician, and then what we need to do is apply these results. Okay, so we don't need to know how to obtain them. Yeah, and you see, since this is an integration, right? That's why I said that Laplace transform is linear. And the reason is because integration is linear. Okay? Because Laplace transform, right, is doing this integral. Okay, it's doing this integral. And you know for the fact that integrals are linear operations. Okay, for example, I give you 4x squared plus 2x, right? So is it, first of all, this integration can act on the first term and the second term separately, right? So this becomes integral 4x squared dx plus integral 2x dx, right? And then next, you know that constants can be pulled out. Constants can be pulled out. So you see, it satisfies the properties of the Laplace transform. Okay? So, for example, the Laplace transform of 4t squared plus 2t. So similarly, you can let the Laplace transform act on the first and second term. Okay? And then after that, you can pull out the constant as well. Okay? So that's why Laplace transform has this linear property. Because Laplace transform, by definition, is a special type of integration. And integration itself, it is linear. Yeah. Okay, so that's how you can remember why Laplace transform has this property. Okay, so now we can finally dive right into the questions. Okay, so use the table and this linear property to work out the Laplace transform of, let's say, this first function. Okay, so let's take a look. So question A, we want to find the Laplace transform of this. So okay, if you take Laplace transform on both sides, you will get this, right? So remember, this by definition is f of x. Okay, and how do you deal with this? Okay, so to deal with this, right, we need to split up this exponent into uh two okay two separate terms. Okay, so what do I mean? Remember the laws of indices, which states a to the m plus n is equal to am times an. Okay, so what we need to do is split this into e to the a times e to the minus bt. Okay, so I'm just basically applying this property of indices. They say a is a constant, right? So this is a constant. Oh, sorry, I forgot my Laplace. Okay, so I split this into this, and then since a is a constant, and also e is a constant, so a constant to the power of constant is also a constant. Okay, so we know that entirely this term here is a constant. If it is a constant, we can pull it outside of the Laplace transform. Then what we're left with is this. So how do we do this? What we need to do is you use the Laplace transform table. So we need to look at the Laplace transform, and can we find any function which looks like this, e to the minus bt. So let's go and have a look. So in the first column, which of these looks closest to e to the minus bt? Okay, it cannot be the first one, cannot be the second one. Looks like the best choice we have is this one. Why? Because it has e to the something. Okay, e to the something. We also have e to the something. Okay, so that's why we will focus on the third entry. Okay, so what does the third entry say? The third entry says Laplace of t to the n minus 1 e to the at is equals to n minus 1 s minus a to the n. Okay, so that's what the second row, sorry, the third row is telling me. Okay, so that's what the third row is telling me. So we're focused on this one. Now, how do we apply it to our function here? So we want e to the minus bt. Okay, so we need to draw some similarities. So in our case, right, our a is actually negative b. Okay, so in our case, a is equal to negative b. Then what else? You see, in front of e here is this t term, t to the n minus 1. Can we make a t to the n minus 1 in front of him? And the answer is yes, we can. So we have this, right? how can I force out a t to the n minus 1 here? Okay, and the answer is this. This here is actually an invisible 1, right? I didn't change anything. 1 times e to the minus bt is still e to the minus bt, so I haven't changed anything. And you know that 1 can be written as t to the 1 minus 1. Okay, why can I claim that? Because t to the 1 minus 1 is actually t to the 0. Let me clear this away first. And then t to the 0, you know, is 1. So I still didn't change anything. Therefore, it is still true. Okay, I haven't changed any meaning. So we have identified that n equals to 1 here. Okay, so now we need to sub in whatever we have. So what do I mean by sub in? We need to sub n equals to 1 and a equals to minus b into this expression here to obtain our f of s. Okay, so therefore f of s is equal to 1 minus 1 over s minus minus b to the power of 1. Okay? And don't forget the factorial here. Okay, so at the top, right, is 0 factorial. 0 factorial is just 1. Then at the bottom, we have s plus b. Okay, so this is our function. Okay? This is our function. I mean, our time domain function. So at the end of the day, this will become a times 1 over s plus b. Yeah. Okay, so this is our answer. So this is part A. Now let's take a look at part B. So part B, we're given the function f of t equal to sine omega t plus delta. Now, how do we deal with this? How do we find the Laplace transform of this? So Laplace transform both sides. And then, so this one will become f of s. Then how do you deal with this? So we need to do some tricks related with this sign. Recall that sine a plus b is equal to sine a cos b plus cos a sine b. What do you call this? You call this the compound angle identity. You can also find this in your formula sheet. Okay, so if you do that, okay, apply it to this case. So this is a and this is b. So what you get is sine omega t cos delta plus cos omega t sine delta. So they've already told us that delta is a constant. Yeah, delta and omega are constants. So why is that helpful? You see, cosine of a constant is still a constant. Sine of a constant is also still a constant. So we can make use of the linear property to pull them outside of the Laplace transform. So this will become cos delta Laplace of sine omega t plus sine delta Laplace of cos omega t. Okay, so essentially, the first term will become this. The second term will become this. Okay? Okay. So now, how do we evaluate this in this? We use the tables. So go back to the tables and check what is sine and cos. So you see, Laplace transform of sine will give you this. Laplace transform of cos will give me this. So just make use of those results. Okay, so if you make use of those results, what will you get? You get cosine delta times omega over s squared plus omega squared. Okay, so this is your part B. So this is your part B. Okay, I've been recording for 1 hour, so let me just stop the video here.